speaker is Anirban Basak.
Thank you, Manjunath. Let me start. So I'll start with an example. Let's consider a very simple example. Let us take a matrix AN of dimension n by n with IID plus minus 1 entries, so random macro entries. So you have this matrix, and there is a very open questions, not so open right now. It has been a long-standing question. What is the probability that this matrix is singular? So the probability that AN is singular. And this question goes back to 1950s. This is very popular in combinatorics or random matrices. And so we want to know what is the probability that this matrix is not invertible. And this is equivalent to saying that, if you look at the determinant of this matrix, this is equal to 0. And this is also same as saying that if you want to look at the smallest singular value, and by smallest singular value I mean that you take you multiply a by x, where x is a unit norm, and you take infimum over the set of all vectors which are in the sphere, and that value is the smallest singular value of a matrix. So as I said, this is a very well-known question. So if you want to answer, if you can answer this question, it just tells you what is the probability that the smallest singular value is exactly equal to 0. And then you may want to have a more quantitative version of this question. So you may want to ask what is the probability that, can you find a probability that the smallest singular value is less than epsilon, given any epsilon? So this is a more of a quantitative nature. So you want to know that what is the probability that the smallest singular value is less than epsilon n, which will go to 0 at certain rate depending on the matrix AN as n goes to infinity. So you know what is the value, what is the probability of this. And possibly the third question, what is the probably the most important question, you may want to understand what is the main reason of non-invertibility of this matrix. I will explain a bit more what I mean by that. So identify the main reason of non-invertibility. Okay. Now to understand this question, what do you mean by this? Let us go back to our question A and see what you know about the probability of n being singular. As I said, this goes back to 1950s. So the first non-trivial result was proved by Komlos and singular. He showed that this is order n to the negative 1/2. Komlos, I think 67. And there are many further improvements. For example, Kahn, Komlos, and Zemredi, they prove it is c to the n for some c less than 1. This was in 95. And then it was improved to 3/4 plus little o of 1 raised to the n by tau and Wu, 0.07. And then it was further improved to 1 over square root 2 plus little o of 1 raised to the n by Burgen, Wu, and Wood, Philip Wood. So this was so this is what we knew like last year. And there is a recent update I will tell you in a minute. And on the other hand, we know that if you have two rows or columns which are identical up to a change of sign, then you do have non-invertibility. So if I want to find a lower bound of the probability that n is non-invertible or n is singular equivalently, this is bounded by the probability that there exist two rows or columns equal up to a change of sign. And you can check that this probability is again bounded below by some constant c times n square times 1/2 to the n. So this is equivalent to saying that this is 1/2 plus little of 1 raised to the n. And this was the conjecture that the probability that n is singular should be equal to 1/2 plus little of 1 raised to the n. So this means that the main reason of non-invertibility for this model of random matrix is that existence of two rows or two columns up to a change in sign. Okay, and this has been proved last month by Konstantin Tikhomirov. So he could show that if you look at the probability that n is singular, this is less than 1/2 plus epsilon to the n for all epsilon positive. So here it proves that if you have a matrix with ID Rademacher entries, then the main reason of non-invertibility that you see in that matrix model is just because of existing of two rows or two columns which may be equal up to change in sign. Any questions or comments at this point? So it says that this is the main reason, but there, you have lower order terms as well. Like you can have three rows or columns having, they are forming a subspan. Forming a span of dimension 2. So these, the ratio. So you're saying that the ratio goes to 1 or not? Yeah, the ratio is not going to 1. So that is correct. So the conjecture is that this is just 1/2 plus little of 1 raised to the n. So this kind of gives you the dominant term in this probability expansion. Now the goal of this talk will be to understand these three phenomena in sparse random matrix models. So again, we'll take a very simple model. So we'll consider our AN now as a matrix with IID Bernoulli P entries. This P will depend on n, and this P will go to 0 as the dimension of the matrix increases. And here we define an event, omega 0, which we call omega 0, is the event that AN can have either a 0 row or a column. And you can note that on this event you have your AN is non-invertible. Okay, and so what you can show here is the following. If you assume that your NP is greater than log 1 over P, then you have bound on the smallest singular value. So it says that the smallest singular value is less than some little c epsilon In the exponent you have, let me first write down the expression, then we'll explain what it means. So it says that if you're on the good event, omega 0 complement. So if you're in the good event that n does not have any 0 or 0 column, then you have a lower bound on the smallest singular value which holds with high probability. And on the other hand, and for this you need to assume that your NP is not too small. On the other hand, if you have, if your NP is less than log 1 over p, then you can just, it is a simple computation that you have a large probability with which your event omega 0 holds. So this is greater than equal to 1 minus c per log n. Now let me explain to you what it really means. Now the first observation that we can make is that if your NP is log 1 over p, then your n times p is roughly equal to log n minus delta n log n, where delta n is about 1. Okay. So this means the following things, that if your NP is like log n plus kn, where your kn goes up to infinity as n goes to infinity, then what the first part tells you that, so then you can also check that probability of omega 0 complement goes to 1. So with very high probability, if your NP is greater than slightly above log n, with very high probability, you will not see any 0 or 0 column. And therefore, when you apply this information to the first part of this theorem, then it follows that probability that n is invertible, this also goes to 1. So you put epsilon equals 0 here, and you know that omega 0 complements happen with very high probability. So you get from here that the smallest singular is exactly equal to 0, which is same as saying that n is non-invertible, probably goes to 0. On the other hand, if we take NP to be slightly less than log n, so log n minus kn, and again kn goes to infinity as n goes up to infinity, then from this part 2 of this theorem, you know that probability omega 0 goes to 1, and on omega 0 your matrix is always non-invertible. So you claim that probability is an non-invertible. This goes to 1. So it says that there is a sharp transition at the threshold log n. And finally, probably the more interesting implication of this theorem is that if you now you're allowed to be NP to be log n plus k, where k is just fixed real, let's say, then for that regime you can check that both omega 0 and omega 0 complement has non-trivial probability. And then you can deduce from this part 1 of this theorem again that if you restrict yourself on this nice event that you don't see in 0 row or 0 column, then your matrix is still invertible. So if you condition on the event that you don't see a 0 row or 0 column, even after conditioning, the probability still goes to 1. Any questions? So this result that I said is just for ID boundary matrices, but this can be generalized to other matrices as well. I'll just give you a few examples. The most natural extension one can think of is to consider ID boundary matrices, but you input the symmetricity condition. So exactly the same results go through. Exactly you have all those conclusions for ID boundary matrices, ID symmetric boundary matrices. So this extends to the case where you have symmetric IID Bernoulli matrices. And moreover, you can extend it to the adjacent matrices of sparse random graphs. So then I'll give some examples. So adjacent matrices. And the most natural example you can think of is undirected Erdős-Srény graphs. So those who are not familiar, probably most of you are familiar. So you have a set of n vertices, and you draw an edge between every pair of vertices with probability p independently of everything else. And another thing that we can extend our results to as is just so everything what I've said just extends to all of these models is a directed Erdős-Srény graph. So how do you construct this directed Erdős-Srény graph? So you take again n vertices, you take any two pair of vertices, you draw an undirected edge with probability 2p, and then you choose a direction uniformly at random. So you choose this direction probability 1/2, you choose this direction probability 1/2, etc. And again for this model, the same results go through, and you have the again same threshold log n over n for the connectivity problem when the connectivity problem is p, and so on and so forth. And there is one more thing that people study in random matrices is a condition number. Condition number is just the ratio of the maximal and the minimal singular value, and it is often of interest to understand the stability of matrix algorithms. So let me define what is condition number. Kappa, so kappa of an is the ratio of singular value and a singular value. And back in 1940s, von Neumann and his collaborators were studying these matrix algorithms, and based on some numerical simulations, von Neumann and his collaborators conjectured that this condition number of a random matrix should be of order n. So what von Neumann conjectured is that if you look at the maximal singular value, it should be order n to the 1/2, minimal singular value n to the negative 1/2, and therefore the ratio should be of order n. Okay. And there has been a lot of work in the last decade and a half, so I'll just mention a few. Suppose you take a matrix with ID entries. You assume they are centered. Let's say they are normalized so that its second moment is 1, and they have finite fourth moment. Then under these three assumptions of the entries of the random matrix, what Mark Riddhipratim and Roman Varshanin showed is that if you look at the smallest singular value, then theta is less than epsilon n to the negative 1/2, dk is like c epsilon plus some c to the n or some little c less than 1. This is the Riddhipratim and Varshanin. This is true for all epsilon positive, non-negative. Okay, now if you combine this result with the result from by Lautala on the maximal singular value, what Lautala showed is that under these four assumptions, these three assumptions on the entries of the random matrix, this was from Lautala. So it says that given any delta, you can find a k such that your maximal singular value cannot exceed k into the negative 1/2 with probability more than delta. So now if you combine these two results on the maximal and the minimal singular value, then you get that the condition number of this matrix, where you have this condition, where these three conditions on the entries, is indeed bounded by order n with very high probability. And if you additionally assume that this entries are sub-Gaussian, then you can improve these error bounds. So I'll not go into that. But this is basically proving von Neumann's conjecture under this very general setup. But these matrices are dense in the sense that you do not see many zeros in the entries. Okay, now a natural question is, what can you do for sparse matrices? For example, can you show that these condition numbers also go this sharp transition at log n over n? So what we did earlier with Mark is the following. So we take a matrix AN, its entries are xi ij times delta ij, n by n matrix, and here xi ij's are IID, let's say they are mean 0 and variance 1, and this delta ij are again IID, Bernoulli P. So if you have this setup, then and if you also assume that your P is roughly of the order n to the negative alpha, where alpha is between 0 and 1, then you can show that the von Neumann's conjecture of the prediction about the condition number holds in this setup. Also, I should say that we also need that some high moments of our xi ij's to be finite. So expression of xi ij to the q has to be finite, where q is this expression 2 times 2 minus alpha over 1 minus alpha. And you can check that if you plug in alpha equals 0, which is the dense setup, then you get back your q to be 4. So in some sense, this is the optimal condition that you can think of to have a bound on the maximal singular value. So if you assume these conditions, then under this set of conditions, we were able to show that the condition number of this matrix is order n with very high probability. And the next question is, how can you push this beyond this barrier where you have this P to decay like n to the some negative power? So if you assume that your xi ij's are sub-Gaussian, centered, then you can actually extend this result, and what you're able to show that if your NP is greater than some big C log n, where C is some big constant, then you have a similar result, not the exactly this result. You can show that this kappa of a n should be of order n raised to the 1 plus a small quantity which goes to 0, some order 1 term over log n. And again, this happens with very high probability. Now, you see, this is almost what von Neumann predicted, except this order 1 over log n term, which goes into the exponent of n. So we believe this is just an artifact of our proof. It should not be there. Any questions? Okay, so this goes up to the threshold where NP is of the order log n, but you have a huge constant in front of that. Now, to extend our result all the way to the threshold log n, we consider on the simpler model where we just take Bernoulli. So here we take n IID, but we take symmetrized Bernoulli. So by this I mean that your Aij equals plus minus 1, each with probability p over 2, and otherwise Aij is 0. Okay, so I do the symmetrization because otherwise you will have a large singular value. So the top singular value will be of the order np, and the rest of the singular value will be of the order square root NP. So just to avoid that, we're making the symmetrization. Now if you have this symmetrized Bernoulli P, then what you can show that, again, now if you recall the event omega 0 which I defined and I have erased now, that if you define this omega 0 such that you have either a 0 row or 0 column, then if you're outside that event, so you're an omega 0 complement, then again you have a similar bound what you got earlier, that kappa n should be of the order n to the 1 plus, again, order 1 over log n. And this holds when your NP is greater than 1 over log of 1 over P. So it means that all the way up to log n, you have this following diagram of your probability space. So here is your omega 0, here is your omega 0 complement. And on this omega 0, because omega 0 tells you that omega 0 by definition is the event that you have either a 0 row or a 0 column. Therefore, on omega 0, your smallest singular value is, by definition, it is 0. So the condition number, you can see, is the ratio of the maximum and the minimum. So the condition number is just infinity here. On the other hand, if you look at omega 0 complement, where you have no 0 row or 0 column, it tells you that your condition number with very high probability of the order n to the 1 plus some little o of 1. Except there is a set of negligible probability. So here we don't know, and outside that's negligible, small set of negligible probability. We know that this condition number behaves as if you are looking at a dense matrix. Because for the dense matrix, we know that this condition number is just order n, and so it says that it almost behaves as if it is a dense matrix. And again, we believe this little of 1 term should not be there. It's just an artifact of our current proof. Any questions? So in the next 10 minutes or so, I'll try to give you a brief idea of the proof, like how one proves bounds on the smallest singular values. So we recall that the smallest singular value by definition is the infimum of the L2 norm of AX, where we take this infimum over the unit sphere. So here what one does, one takes this sphere and splits into two parts. In one part you have vectors that are close to sparse vectors. And its complement. So by sparse vectors, I mean that you have not too many non-zero coordinates. So you split this sphere in two parts. One part is vectors which are close to sparse vectors and its complement. Try to bound the infimum over each of these parts separately. So first let me explain how do we bound the infimum over the vectors that are close to sparse vectors. So first let's go back to the proof. Let's remind ourselves the proof, how one does this thing for the dense matrix. And then I'll show you what modifications do you need to extend the argument for the sparse random matrices. So we take let's say my AN, this is my AN, and its rows are A1, A2 up to AN. And then if I look at the L2 norm of ANX, square of that is nothing but the sum of the inner product of ai and x square of summing over from 1 to n. Now what you do, you pick out any inner product and you want to bound that this is not too small. So find a probability, find an upper bound of the event that this inner product is not too small. And you can check that there exists certain constant c, so that this is less than 1/2, and this is just a consequence of Paley-Zygmunt inequality. This falls from there. Now once you have that, since the rows are independent, so you can apply standard techniques and you can tensorize this bound to get a non-trivial bound for every fixed x. So you just do tensorization and get that this norm of a and x, the L2 norm of a and x, cannot be less than some c prime square root n, some c tilde raised to the n. So this is just very simple. You use this bound, and since these randomness are independent, you get this bound. Okay. Now, what is the problem if you want to carry out the exact same argument as the sparse matrices? Okay. So let me try to explain that. What is the problem if you want to carry out this exact same argument? Okay. So here I did not finish. So how do you go from here? So you fixed an x, then you show that the L2 norm of a and x can be too small. Then, since the vectors are sparse or close to sparse, so the collection of such vectors has low metric entropy, and therefore you can take an epsilon net argument, you can use an epsilon net argument, you can use a union bound, and from this probability bound you can deduce a uniform contour on the infimum of the set of all sparse vectors. So then you just use sparse vectors has low metric entropy, and therefore use a net argument and union bound. Okay. Now, next let's try to repeat the same argument for the sparse case and see where it fails. So if I want to use the same argument for the sparse setup, what I will get is the following. Okay. So I did not define here, so what I mean by sparse vector, that will fix a delta, okay? And you want your vectors to be close to delta in sparse vector, meaning that you have only delta in non-zero entries, and by close you can choose a Euclidean norm. So there is another parameter eta, let's say. So this will show you, this net will show you that you can find a delta and an eta, such that if you want to take an infimum of a set of all such vectors, then you get this exponentially small bound. Why? So then, okay, so this will take care of so this is called compressible vectors, so this will take care of the compressible delta eta vectors. Now you have a separate argument which can be used to control the infimum of the set of all complements of such vectors. So if you can do it for any fixed delta and eta, then the proof can be carried forward. So let's see what happens with the sparse setup. So if you want to, so we want to start with the same quantity, that we want to look at the inner product of ai and x less than c. Okay. Let's not normalize x right now, so we have norm of x here. And since ai's are Bernoulli p, so one can check that the appropriate thing would be to put a square root p here. And if you again apply Paley-Zygmunt inequality, you will end up with something like this. 1 minus p over the square of the ratio of the L infinity and L2 norm of x plus p. So this is again Paley-Zygmunt. Now the crucial thing that we used in this dense setup, that this is bounded away from 1. So that was important. Now you can see that for certain sparse vectors, you can make this ratio to go to 0. So you cannot just readily apply Pelly-Zygmunt, and you cannot apply the standard transformation technique to have a bound on this compressible vector or the sparse vectors. So this is going to split this space into further subparts. So here there will be 1 over p, there will be some delta n, here is n. So this I'm just denoting the support of the vector x. So if we are here, let's call them moderately sparse vectors. And let's call them very sparse. So if you have moderately sparse vectors, then one can show that if you are in this region, then this bound is away from 1. Okay, so this is the length of the support of the x. This goes in this direction. So you pick an x, and you want to see how many non-zero entries in the support of x are. So if you have more than 1 over p many entries in your support, then you can show that you can apply Pelly-Zygmunt inequality, and what you get from here, out of here, is strictly less than 1. And therefore, you can essentially repeat the same argument. You can use this exactly same trick, and you can have a bound to control the infinity over all those sparse vectors, which has at least 1 over p many entries in its support. So here you apply Pelly-Zygmunt. And proceed as earlier. Now to treat these very sparse vectors, you need a different argument. So I'll explain to you what is the different argument. So the idea is the following. Here is my A, here is my X. Let's assume that, for simplicity, let's assume that all the non-zero entries are here, and this is 0. This is my X, this is my AN. Now what we want to do, we want to multiply this AN by X, so therefore this part of the matrix doesn't come into play, the right side. Now what you want to do is something following. So we want to say that out of this rectangular matrix, we can extract a very large submatrix such that every row has exactly 1 non-zero entry. This means when you multiply by x, you just pick up one coordinate of xi, one particular coordinate of x. And therefore, since our matrices are integer valued, they can be, all the entries are either 0 or 1, so you just get back xi for the particular I. And you know that the norm of this is 1 because you're on the unit sphere. So, and if this matrix is large enough, then you accumulate a lot of norms. And that gives you a bound on the lower bound on the L2 norm of n times x. So this is the basic idea. Now how do you get this? For that you need to use expansion properties of your graph. So this will create a graph because this is a matrix of zeros and ones. So you have an underlying graph there, and when np is not too small, meaning np is about log n or log n minus log n, then you can show that this graph is nice enough so that you can use the expansion property to extract such a large matrix with this property. What are the? Okay, so the size that we need is something like this. So we need this to be, I think, if I remember correctly, inverse, and this you need to be of order n times p, because you want to have this norm which is of order square root np. So you want to collect one from each of these entries, and if there are np many rows, then since all are this will give you a norm of order square root np. And this you need to do for uniformly for all x. So given a x, there will be some submatrix. Out of that submatrix, you need to pick a matrix with these properties of these sizes. Okay. So for here, I will, yes, yeah. Okay, right. So basically, here I need to deal with sparse vectors as well as vectors which are close to sparse vectors. So I need to show that there is a small part which doesn't cancel the part that I'm accumulating from this norm. So basically what I drew there is not entirely correct. So you have this matrix where, submatrix where you have exactly one ones and 0, rest are entries 0 per row. And you also have a submatrix which is also quite large, so that you have all zeros. So that does not bother us because your P is small, you can get that. The crucial part is that you have this submatrix where you have exactly ones and rest of the 0, and you have a large collection of rows. So basically here, to say it briefly, use expansion properties of the underlying graph. Now it remains to control with vectors which are not sparse, meaning that you have support. The support of the vectors is at least as large as delta n. So there I will not go into too much of a details. So there is a standard technique which is just by applying variation theorem to bound infimum over non-sparse vectors. Use variation theorem. And I will stop here. Thanks. Yes. Yes. So that question we haven't looked into, so I do not know what is the, after you condition that you do not have 0 or 0 columns, so I guess it will be some low dimensional event, like, like what you see in the dense setup, like what you did, that showing that, that if you have a dense matrix, you have plus minus and different entries, then the main condition is coming from the signs. Then maybe some low dimensional contribution, like you have some small number of collection of rows that produces some subspan of smaller dimension. That my guess would be that will be the dominant terms, but I do not know exactly what it is. Yeah. So I do not know. We did not think in that direction, so I do not know what it should be.